So we'll start with the electromagnetic radiation. For understanding of electromagnetic radiation, the first thing which we would be discussing is the types of waves. The first type is the transverse wave, this one. Now what you can see about this wave is that the movement of the particles is perpendicular to the direction of the wave. See, if this is the direction of the wave, the particles are going to move like this. So the movement is perpendicular to the transmission of the wave. Now in comparison to the transverse wave, we have the other type of wave, which is the longitudinal wave. Longitudinal wave, we have the movement of the particles which is in direction to the progression of wave. So in this example, if you can see that the particles are moving in this direction, compression, so the particles are more closer to each other, whereas in the rarefaction they are separated. But the movement is in the direction of the wave, not perpendicular. In the transverse wave, the movement of the particle was perpendicular to the progression of the wave direction. So the electromagnetic wave is basically an electromagnetic disturbance which is consisting of oscillating electric and the magnetic fields. So the Faraday's law tells that if you have a variable electric field, it can induce a magnetic field which is perpendicular to the electric field, and if you have an alternating magnetic field, it can induce an electric field which is of course perpendicular to the magnetic field itself. So if any of this field is going to change, it is going to induce the other. So this makes the electromagnetic field or wave self-propagating, and they don't need any mass to travel through. So that's why they are traveling across large distances and they don't need any medium, and they can travel in space. So as you can see that they are the electric and magnetic field are at right angle or perpendicular to each other. So this makes this wave a type of transverse waves. So this is a graphical presentation in an animated, which is taken from Wikipedia, and you can see that the amplitude and the electric fields and the magnetic fields, which is B, are alternating with each other, and you can see that if the amplitude of E increases, so does the amplitude of B. So from now we will be discussing a few fundamental definitions about the waves, and you can see that we will be discussing the five main topics, and the first is going to be the amplitude. So amplitude is going to be defined as the maximum value or the maximum displacement from the base, and it is the peak field strength as well if we discuss the electromagnetic wave. So the maximum displacement is the amplitude, wavelength, and it is a distance between one peak to the next peak. So this constitutes basically one wave, and the length of this is going to be measured in meters, and it is named as wavelength and is denoted by the lambda. The second is, so now moving to the next, which is the period. It's simply the time interval between these two successive crests, and it is measured in the seconds. And the next is the frequency, which is the number of wave peaks passing within a given point. Say we take this point, and how many number of the waves or the successive crests have passed, those are the frequencies. Say for example, if there are 100 peaks passing per second through this point, so the frequency would be 100. and this is calculated in hertz, and 1 hertz is equal to 1 peak passing through any given point. Now we come to the velocity. For the velocity we have a formula which is written as velocity is equal to with frequency, which is the number of the peaks passing through any given point, into the wavelength, which is the measurement of one crest to the other crest, and when we multiply this is the speed of that wave. And you know that the electromagnetic waves have a constant speed, and that we have just discussed is 3 into 10 to raise to power 8. And all electromagnetic radiation, whether it is X-rays, gamma rays or light, these all are going to be showing a fixed velocity, which is 3 into 10 to raise to power 8 meter per second. So discuss the wave properties of the electromagnetic radiation. It is also seen that the X-rays and gamma rays can show particle-like properties as well. To explain those, we consider them as a packet of energies, or which are known as photon, which are going to contain a certain amount of energy in them, and the energy is going to be proportional to the frequency of wavelength. And now if we can see that these are suppose an example of photon, and now if you can see that if there is a beam of EM radiation coming from, say, from gamma or from X-rays, so they are basically a stream of photons of might be different or same energies depending on their source. So to discuss this further, free energy of any photon is going to be directly proportional to the frequency, and to make this a constant value, we add an h. E is equal to hf, where h is going to be Planck's constant, and it has a value of 6.6 into 10 to raise to power minus 34 joule second. Okay, so this is going to be a constant value, and this is going to be used for driving the energy of any photon having a certain number of frequency. But as this value is going to be a too minute value, so what we do is we use the value of electron volt EV to denote the value of the energy of any photon. So it could be from, say, like 30 keV photon, or could be 120 keV photon, which we will be discussing in the coming lectures. And one important thing here is that if it's a sort of a gamma source, so most of the photons produced are of identical energies, whereas in X-rays there would be variation in the energies of the photons, and they will have a rather spectrum form of energies. So in this image you will see that this is a wave pattern of one photon, and this is a wave pattern of another photon. So this is going to show you a less energy, because obviously it has a larger wavelength, but the frequency is going to be less, or almost half of this wave, which is going to show you within a given time that a double number of crusts are present within this wave. So just to make an idea, like this photon is, these both were photons, so this photon would, say for example, is going to have an energy of 20 keV, for example. So this is going to be approximately 40 keV energy photon. So another thing what you have seen is that the short wavelength is going to be more associated with high energy photon and the higher the frequency, higher the energy of photon, whereas in this case you can see the wavelength is larger but the energy is going to be less because obviously you have less frequency. So in summary, we can say that short wavelength radiation has high frequency and high proton energy, and long wavelength radiation has low frequency and then obviously low photon energy. Okay, so this spectrum is again from Wikipedia and is going to show you a distribution of the electromagnetic waves, how they are spreaded. So starting from this part of the spectrum, which is the visible, which our eye can appreciate. So we have different colors, but only this part of the spectrum is visible to us. Below this and above this are going to be, depending on the frequency of the photons, there are going to be different energies. Towards this side, the upside, the frequency, this is the frequency, so frequency is increasing, and you can see on this side there is the wavelength, and this is the frequency. So the wavelength is basically decreasing as we go up, whereas the frequency is increasing, and this is going to be having a direct relation because the velocity is constant, so we can't change the velocity. So if one is going to increase, the other is going to decrease. So as we increase the frequency, the energy of the photons is going to increase, and now we can see that after visible light we have some ultraviolet spectrum, and then we have the X-rays and the gamma rays. So these two parts are the most important to us in the imaging. So and these are the ionizing radiation as well. The ionizing radiation is the X-rays and gamma rays which have photon energy sufficient to ionize atoms. Just two more important concepts. One is that wherever you have a source, you are going to produce some number of photons, and say they are traveling in this direction. So whatever the number of photons are being produced, if you calculate them over time, it is known as photon fluence. So whatever number of photons we are going to produce, it is going to, over a certain time, if you count them all, the number of photons, that's known as photons fluence. And now if you count the number of photons in a unit time, so you apply that within certain time how much photon is going to pass in that area, so that is going to known as photon fluence rate. So by adding time, we have now developed photon fluence rate. From a number of photons, I have a photon fluence, and then I made a photon fluence rate. So now for each photon, if I count their energy, say for E1, E2, E3, E4, E5, and collect them all, and these sum of energies is going to be known as energy fluence. And if we apply some time, say for when we want to calculate in 1 second, so that is going to be known as energy fluence rate. This is the flow of the energy by those photons within a certain area within a certain time. So from photon fluence, we derived photon fluence rate. From energy fluence, by calculating the energies of each photons, we made the energy fluence, and then by adding the time to it, like say in 1 second, we made up the energy fluence rate. Now the issue is that we cannot stop all the photons and calculate that energies, but we can have a sort of an indirect measurement, and that is known as air karma rate. So this is the indirect measure of the flow of energy by all photons through that any area in a given time. And this, the karma stands for kinetic energy released to matter. And so we'll be discussing this karma. So this air karma rate can be used to calculate the radiation doses and all those things, and we will be discussing this. in detail as we move forward. And last topic of this talk, and that is going to be the inverse square law. So inverse square law basically states is property of the electromagnetic radiation, and it states that first we have known that they are all going to travel in a straight line, and then just keeping in mind the energy fluence rate, which is also the beam intensity, that is also going to reduce because the beam is going to scatter out. So as you can see from this source, as it travels, it is going to cover more area, and as you double the distance, the area is going to increase by square. So like the 2, when it's going to be 2, it's going to be 2 square, and it's going to be 4. So the beam intensity, which was 1 at this level, is going to be 1 by 4 at this level in one given area or the same area. Now what happens is, like if the beam travels say for 3, so 3 square is going to be 9. So we have the same intensity split it up into the 9 different compartments. So this is going to give you a value of say 1/9 of the intensity which was present in this block. So and if we take it up to 4, so it's going to be 16, and then the radiation has been reduced to, or beam intensity will be reduced to 1 by 16th.